Hello everyone, I'm Vishwajit and I am currently pursuing my second year in Artificial Intelligence and Machine Learning at Savita Engineering College. Today we'll be covering Linux processes and the three core process APIs fork, wait and execute. Over the next few minutes you'll learn what a process is, how processes are created and managed in Linux and how to use these process calls to implement simple but powerful process control in your programs. Let's begin. Firstly, what is process? A process is a program in execution. It's what the operating system creates and manages when you run a command or start an application. A process consists of several parts: the program code itself, and then the process data and heap, the stack of for function calls, and CPU registers holding the current execution state, and the data structure called PC block, or in short PCB, which the kernel uses to keep track of the process. And each process also receives an identifier called process ID, in short PID. This PID is how the kernel and other programs identify and refer to the process. For example, when you type ls in the terminal, this shell spawns a process to execute the command, and this and when you compile code with GCC, the command runs as another process, and so every invocation of a program is typically represented by a process while it runs. So process move through a life cycle. They don't just appear or disappear. There are few standard states that you should know about the process life cycle. So first, new. It is the process that is being created and the resources are being allocated. Second, running. It is the process that is currently executing the instructions on the CPU. Third, waiting or blocked. The process is being waiting for some event like input output device to complete or a child process to finish. Fourth, ready. The process is ready to run but it is waiting in the queue for the CPU schedule to pick it. And the fifth, terminated. The process has finished executing and its resources are being reclaimed. So example, for think of it like a traffic flow. Process wait in different lanes and the scheduler decides which one to go next. Modern tools like PS, top, and graphical system monitors let you inspect process states in real time. In Linux, processes are organized into an hierarchy. Every process except the first one is created at boot as a parent access. When a process creates another, the new one is the child, and this parent child relationship forms a process tree. For example, your shell process might spawn GCC to compile code, and GCC might spawn the linker or the other helper programs. Each is a child of the process that is launched it. And to inspect running processes and relationship, you can use psef command to list processes with the PIDs and the parent PIDs, or ps-tree command to use the tree view. In short, Linux uses the parent-child model to manage ownership, signals, and cleanup. So now let's get into the code of fork. Fork is the system call used to create a new process. When a process calls fork command, the kernel creates a child process that is at the moment of the creation and almost an exact duplicate of a parent. So that means the child starts executing at the instruction right after the fork command call. So the key to use fork is its return value in the child process. Fork returns 0 and the parent, it returns the child's PID, which is positive number, and if it returns a negative value, it means the fork is failed. This lets you write a conditional code to distinguish between the parent and the child behavior. And here's an example of the fork command. I'll read it out. PID is equals to fork. If PID equal to 0, printf child process, else printf parent process. When you run this, you usually see both print statements, one from the child and one from the parent, but the order can vary depending on scheduling. Next is wait, which helps coordinate parent and child process. If a parent wants to wait for the child to finish before continuing, it calls wait command or wait PID command. Without calling wait, a finished child becomes a zombie process. It's dead but still a dead entry in the process table because the parent hasn't read the exit status. Here's a simple pattern: PID is equals to fork. If PID equal to 0, printf child executing, else wait null, printf parent resumes after child finishes. In this code, the parent blocks inside wait null command until the child exits, preventing zombies and ensuring the parent can gather the child's exit status. So the best practice is that you can use wait PID command when you need more control, such as waiting for a specific child or non-blocking waits. Execute is different. It does not create a new process. Instead, execute replaces current process image, code, data, and stack with a new program. And typically, you fork first to create a new process. Then inside the child you can call the execute command to run the different executable in that child. So there are several executive variants like exec L, exec V, exec P, and exec VP. They differ by how you pass the argument list and whether the path is searched. Here's a common pattern: PID is equals to fork, and if PID equal to 0, exec L where slash bin slash ls comma ls comma minus l comma null, else wait null. In this example, the child becomes ls minus l and the parent waits for it to finish, and if exec succeeds it never returns. If it fails, it returns -1 and sets error. Let's put all together into a common workflow you'll see in many programs. The typical pattern for launching another program is the parent calls fork to create a child. Inside it, the child process calls exec to replace the child's image with a new program, and the parent calls wait or the wait PID to wait for the child to correct its exit status and avoid zombie processes. Visually, parent is fork and the child is exec, and the parent uses the wait to and then parent continues. This pattern separates concerns that parent remains supervisor and the child becomes the worker running the executable. Before we finish, here are some common pitfalls and best practices. So first, always check on return values. System calls can fail. Check fork, exec command, and wait command to and handle the errors gracefully, usually by printing p error and existing if needed. And second, avoid unnecessary forks. Forking is relatively cheap, but unnecessary duplication of processes wastes resources and complicates logic. Third, prevent zombies by calling wait command or wait PID command or handling the threshold properly in more advanced programs, and use wait PID when you need to wait for a specific child or when you need for non-blocking behavior. And finally, use execute command correctly. Remember that execute command replaces the process image in any code after a successful executable won't run. So if executable returns, it indicates an error. Always handle that case. To summarize, we learned what Linux process is, how process transition to lifecycle states, and how Linux organizes the process into parent-child hierarchy. And we also saw the three key APIs: one, fork it to create new process; execute to replace process image with a new program; and third, wait to synchronize parents with the children and prevent zombies. So for practice, try writing small programs that use these calls. Experiment with multiple forks, combine fork and executable, and use get PID and get PPID commands to print PIDs during execution, and that AND's practice is the best way to master process control in Linux. Thank you.